50 people, so I guess it's a good crowd for July 28th. All right, everyone, so welcome back to the CRM Camp seminar. It is our sixth seminar of this initiative, of this project, and we're very happy, and I'm personally very happy today to introduce Nilima Nigam from Simon Fraser University. So she's a professor there of mathematics. She moved as a Tier 2 Canada Research Chair from McGill University in 2008. She completed her PhD at the University of Delaware, and she was an industrial postdoctoral fellow at IMA in Minneapolis. And after that, she started getting interested in a wide variety of mathematical subjects. And these days, she's thinking about problems at the interface of numerical analysis and spectral geometry. And I believe this is what she's going to talk about today. And she's going to talk about modification of Schiffer's conjecture and a proof via finite elements. So please, Nilima, it's all yours.
Thank you very much, Jean-Philippe, and thank you all for coming out. It's quite remarkable that people actually sign in for long distance talks in different time zones, so I'm very grateful. So this is a rather quirky topic, and I'm grateful for the opportunity to talk about it. I have to warn you that there might be a soundtrack to my talk. So I have construction going on next door and my dog gets upset. So between the two things, periodically I might need to mute myself. Anyway, so this is joint work with Bartek Siodea, who is now at ADRO, and Ben Young, who is at the University of Oregon. And this is a project that we began together, I think almost 7 years ago now. So we worked on this, we put it on the archive, and then we kind of forgot about it. But somebody pointed out to us that, hey, you never actually did write this up and send it out. So we did write it up and send it out properly, and it should be on FOCM. I think it is on FOCM now. All right, so what is this talk about? Briefly, I'd like to go over a short background on what I've been thinking about, and to tell you about Schiffer's conjecture and some modifications of it. And then the heart of the talk is a proof for a modification of Schiffer's conjecture on a regular pentagon. And part of this proof, the numerically validated part, is to verify that a certain eigenvalue on a certain domain is bigger than a constant V. So I'll tell you why this strange inequality arises, and I'll tell you what the domains phi of d are. I'll tell you what the constant is. But the gist of it is that there is a very famous old conjecture. There is a modification thereof. We try to prove it on a range of regular polygons, and the Pentagon, as is often the case, was the hardest. And for that particular case, we had to reach to validated numerics. And where the validated numerics in particular became very helpful was in verification of this inequality. All right. So this is now preaching to the choir in this camp, but I just thought I'd review the discrepancy between what we try to do when we're proving things, usually on pen and paper, and how we do it if we're using validated numerics. So for example, suppose we wanted to find the eigenpairs lambda and u for some kind of an infinite dimensional operator A, which maps some infinite dimensional function space calligraphic H to H. So there we understand what we mean by finding the eigenpair u and h, u and lambda, sorry, where u is going to be an infinite dimensional object and lambda might be a complex scalar. Once you start to try to discretize this object, you end up with a finite dimensional subspace typically. If you're lucky, it's a subspace of H, but H sub n does not have to be a subspace of H. The eigenpairs that you look for will be eigenpairs of a problem now in a finite dimensional space. You have to represent the object of interest in terms of some vectorial object, say in a finite dimensional Euclidean space with scalars that are complex, so in Cn. So then the game becomes you're looking for constants in Cn and an eigenvalue C, so that a matrix eigenvalue problem is satisfied. So you have the eigenvalue problem, A and M acting on a vector is lambda n, the approximate eigenvalue, times B and M times Un. So this is what we think about. And then when we actually finally compute this, we're doing this in finite precision arithmetic or with interval arithmetic, typically using an iterative method. Because unless you're very lucky, you cannot find the eigenvalues lambda n of this object exactly, right? So whatever method you use, you will end up with an approximate eigenvector U tilde and an approximate eigenvalue L. And these are objects which somehow have to be related back to the original object of interest, U and lambda. So there's a fair number of steps in between, and I think all of you have far more expertise in this than I do. Being aware of these different steps and how exactly the errors of approximation accumulate is important and of interest. All right. So this talk specifically is about locating eigenvalues for mixed problems. So suppose D is this very strange polygon, and I'll tell you where it arises. I would like to find the mixed eigenvalue of the Laplacian, where I'm going to denote by lambda sub k superscript mixed the eigenvalues of the Laplacian, which have 0 Neumann data on blue curves and 0 Dirichlet data on the red edges. So whenever you see a blue curve, think Neumann 0, and whenever you see a red curve, think Dirichlet 0. So what do we know about this problem? Well, we know that provided you have a little bit of the red edge, non-zero content, then the first eigenvalue is strictly positive. And then you have an ascending sequence, which only accumulates at infinity. If we had only Neumann data, then the first eigenvalue is 0. And what we wish to do in this talk, yet again, is to show that the smallest mixed eigenvalue on such domains, on such specific domains, and I will tell you what those are, is bigger than a constant v for a given fixed v. All right.
So Nilima?
Yes.
So the v is like, there exists a v such that that's happening. I mean, is there any, in the conjecture, was the v like given a value, or the v was, there exists a v?
No, so when I'll get to the conjecture in a bit. The v arises during the strategy of proof. The v is not integral to the conjecture. In fact, you could try to prove the conjecture using other strategies, which are completely analytic. We've tried. The v we constructed comes about as a consequence of the particular strategy we've employed.
Okay, thank you.
Mm-hmm. All right, so my notation is that I've got a domain in R2. There's no interesting metric beyond the Euclidean metric. Nodal domains are domains which are connected subsets where the eigenfunction has one sign. So it's either positive or negative, it doesn't matter. And a nodal line, this is an object that will be of interest, is a zero-level set of an eigenfunction. There's the background sound. All right. Alpha, shh. All right. So here's Schiffer's conjecture. It's a very old conjecture, and it states that if you have the Neumann problem, the full Neumann problem on a domain omega, and if U is such an eigenfunction, if the boundary of your domain is a level set, in other words, U is identically a constant on the boundary, then either the boundary is the boundary of a disk or the function is identically the same constant. So this is a very, very unusual result if you think about it. It's telling you that if you have any of the Neumann eigenfunctions of a domain possess the property that they become constant on the boundary, then the domain must be a disk. Otherwise, you've picked up the constant. So it's a very odd conjecture to think about it. To the best of my knowledge, it was first reported in a talk by Yao in 1979, but it's a well-known conjecture. It seems plausible. So I've tried to show you a few eigenfunctions on a square, an ellipse, and a disk. Okay, so I've plotted the first 5 non-constant eigenfunctions. And you can see that in each of the square cases and the ellipse cases, the boundary is not a constant. Whereas for the disk, by the time you reach the 5th non-constant eigenfunction, you do acquire an eigenfunction which is identically a constant on the boundary. So there's a lot of symmetry happening here, right? You want the function to have 0 normal trace on the boundary and to be a constant on the boundary. So it makes sense that you have this happen on a disk. And it would make sense that perhaps this does not happen in the absence of a lot of symmetries. Okay? It seems plausible. But the conjecture is still open. So it seems so natural, it seems so reasonable, and yet it is still open. The conjecture is open. It's not just a toy problem in spectral geometry. There are deep connections between Schiffer's conjecture and the Pompeo problem, also to stationary solutions of the Euler equation. And there is a certain relationship, somewhat more tenuous, of the convergence of solutions to the Navier-Stokes to that of the Euler equations in the vanishing viscosity limit and Schiffer's conjecture. Okay? So settling Schiffer's conjecture would actually be a pretty important result, but that's not what we did. There are some sample results just to give you a flavor of the fact that this is an active area of interest in spectral geometry, but the results tend to be very specific. So there's a paper, for example, in 2011 that says that if you have a connected domain with smooth boundary, already this is a restriction that's not in Schiffer's conjecture, and you have u being a constant on the boundary, and if the eigenvalue to which this is associated is less than the 8th eigenvalue, or if you have certain restrictions on the domain, then omega must be a disk. So this is very, very specific. This is, the proof is very interesting. It's quite hard. Nonetheless, this is a modification of Schiffer's conjecture. Here's another direction in which you could modify it. So you could relax the constraint that u becomes constant on the boundary. Such a modification was proposed by Hoffman and Ostanov, who said that on a rectangle, if you have any of the Neumann eigenfunctions, which is strictly positive or strictly negative, it doesn't matter, right? There's a sign there that doesn't matter. So any non-constant eigenfunction which is strictly positive, well, you can't have that. It must be a constant. So any Neumann eigenfunction on a rectangle which is strictly of one sign on the boundary must be a constant. Okay. So this is a tractable modification. It's a relaxation of Schiffer's conjecture that we started thinking about. So the modification is as follows. Let omega be a regular polygon with a fixed number of sides n. Okay. The claim is if n is equal to 3, so on triangles, on the equilateral triangle, if you have any Neumann eigenfunction which is less than or equal to 0 or strictly bigger than or equal to 0 on the boundary, then u must be a constant. The case of the rectangle was settled by Hoffman-Ostanov. And then the claim is that for n bigger than or equal to 5, there is an eigenfunction which is strictly of one sign on the boundary and not a constant. Okay. So this is what we're after. For n bigger than or equal to 5, for pentagons and above, you can find an eigenfunction strictly of one sign on the boundary and not a constant. All right, So the conjecture is a theorem for the triangle. This appeared in a paper by Ciudea, and we also had a preprint on this in 2015. And here the strategy that we used was combinatorial. The case of the rectangle was settled by Hoffman-Ustinov. On the hexagon, on the regular hexagon, there's so much symmetry that you can do an explicit construction. For n bigger than 6, we can use symmetrization and the Courant nodal line theorem. So again, anything that's like 6-sided, 7-sided, 8-sided and above, that's done. The triangle is done. The square was done by Hoffman-Ustinov. The pentagon, none of our strategies worked. So we want to show that the modified Schiffer's conjecture holds on the regular pentagon. Okay? So that's what we're after. All right. Once again, it seems really plausible. So what I've done here is shown you the fourth and the fifth Neumann eigenfunction of the Laplacian with Neumann data on the boundary. The fifth eigenfunction, you can see it does not change sign. It's strictly of one, it's of one color on the boundary. Okay. And take my word for it, the curve in blue is where the 0 is. Okay. Now, when I gave this talk at a numerical analysis meeting a few years ago, people were like, okay, it's done. You're done, right? You've shown this using a finite element calculation. The picture is right there, finished. But of course, this is not a proof. This is a very strong indication that this conjecture is correct on the Pentagon, but it's not a proof. Okay. So what is the strategy we're going to use? The strategy is we're going to use the symmetry of the Pentagon as much as we can. We're going to split it into 5 congruent isosceles triangles. And then each of these, we're going to split into 2 congruent right angle triangles. So let's focus our attention over here. So we're going to work on the triangle AFB. And we're going to split it down the middle. So we're really looking at BOF, the triangle that I've indicated in the blue line here. Okay. So that's the triangle I'm going to work on, because if I can figure something out over here with Neumann condition on this edge and on this edge, I can reflect around the side BF 10 times, and then I'll be done. Okay. So to show that we have a non-constant eigenfunction, which does not change sign on the boundary, I'm going to use 2 steps. Okay? I'm going to show that a nodal line for the second eigenfunction on the triangle, so the first non-constant Neumann eigenfunction, it has to start on the long edge, and I have to prove to you that it ends on this edge OF. And then I'm going to reflect it, which means that after reflection, I'm thinking I should get a picture like this. The nodal line should not touch the outside of the pentagon. Okay. So if I started out with something positive here and something negative here, upon reflection, that's what I'm going to have. And so I'm going to end up with an eigenfunction that's strictly positive on the boundary. So the goal now is to try and show that the nodal line does not touch the short edge OB. Okay. So there are some known analytic results which are important. So there is a statement by Ciudea which says that the nodal line for the second Neumann eigenfunction on a triangle must start on one side and end on another side, or a vertex connecting the other 2 sides. In other words, you cannot have a loop that ends back on the same edge, because that would not work. There's another interesting result due to Attar and Birdsey in 2005. And this is about the signs of the derivatives of this eigenfunction. So it says that the x derivative of the eigenfunction and the y derivative of the eigenfunction, they must have opposite signs on a triangle, and they're never zero, which means that you have no local maxima inside the domain, right? So here's a picture of the vectors of the gradient. You can see that they're pointing down, okay? So the x derivative is strictly positive in this picture, and the y derivative is strictly negative. If you put these two results together, what you arrive at is that the nodal line for the second Neumann eigenfunction on this triangle must be the graph of a strictly increasing function. So it has to touch the long side BF, and it must be the graph of a strictly increasing function. So it could still start on this edge and go up. It could start on the bottom edge and go up. It could start at the vertex and go up. It cannot start at BF and end at BF. Okay. All right. So the theorem that we prove, or the main key theorem in our proof, is on the triangle that is obtained from the regular pentagon, if U2 is the second Neumann eigenfunction, so it's the first non-trivial eigenpair, then the nodal line for this eigenfunction must touch the long edge and cannot touch the short edge. Okay? The steps in the proof are, well, the first step is already done, right? You know that the nodal line must touch the long side from the lemma, and now we need to show that it touches the short side. So that statement in red is the only step left to show. If we can show this step, then we will have proved the modification of Schiffer's conjecture on the regular pentagon. All right. So we tried many things, and one of the key tools that we ended up using was a domain monotonicity result. And this may be familiar to many of you, so I apologize. But the statement is that if you have two domains, D1, which is connected in D2, both open, and the Neumann boundary, or part of the Neumann boundary of D1, is a subset of the Neumann boundary of D2, then if you put Dirichlet data on the other bits, your eigenvalue decreases. Right? So growing the domain decreases the mixed eigenvalue. Okay. It's similar in flavor to similar results for just the pure Dirichlet eigenvalues. So growing the domain with a shared Neumann face decreases the eigenvalue. So here's a corollary. Suppose I start off in this triangle APB. Suppose I construct a Neumann eigenfunction there. Okay? So I'm on this big triangle and I've constructed a Neumann eigenfunction. Suppose I have a nodal domain PWQ. So my eigenfunction vanishes along the line WQ, and it's of one sign in here. Okay? The claim is, if I could find another domain that contains this nodal domain, so if I could find a D2 that contains this nodal domain, such that the Neumann pieces of my nodal domain are a subset of the Neumann pieces of the grown domain, and suppose moreover that the mixed eigenvalue was bigger than the Neumann eigenvalue on the whole domain, okay? Then it must be the case that this line here, this dashed line, must intersect the red line. That's the only possibility. In other words, this situation that I have shown for you in this diagram, in this situation, the nodal domain PQW is contained in the grown domain PRS. RS does not intersect the nodal line WQ. Therefore, the eigenvalue on PRS must be less than or equal to the mixed eigenvalue on PQW, which is the same as the Neumann eigenvalue on the whole domain. Okay. All right. So get a quick look at the time. So our goal is to try and show that this is what happens on the triangle from the regular pentagon. This is the situation we want. We're going to prove this by contradiction. We're going to assume this is not what happens. We're going to assume that instead the nodal line cuts the short side OB. Okay? So we get a nodal domain omega 1. We're going to grow that nodal domain by adding this other Dirichlet piece. And we're going to show a contradiction. So we're going to construct this grown domain using a very interesting greedy algorithm. I will not give you the details of the greedy algorithm. I'll just show you a flavor and pictures of how we do this. So we're going to construct a sequence of these grown domains. Now, we know that the mixed eigenvalue has to decrease. It has to be less than or equal to the eigenvalue of the Neumann problem on the whole domain. However, numerically, we will show that it's actually strictly bigger than the Neumann eigenvalue. And that's where this V comes in. We find a constant that's bigger than the Neumann eigenvalue on the triangle, but still it's smaller than the mixed eigenvalues of all these grown domains that we construct. And this will yield a contradiction because this is a theorem in red. This is what we show. Therefore, our assumption must be false. Now I'm going to prepare myself to work with validated numerics. And I really dislike the idea of working on anything except objects with rational coordinates, right? I don't want to be working with tan of pi over 5. So this is the triangle I have. This is OBA. The angle here is pi over 5. What I construct are two additional triangles, T prime and OB dash is a rational. This is tan of pi over 5. So I'm choosing OA to be 1 in all three cases. Okay. So this is a rational length. This is tan of pi over 5. This is another rational length of 93 over 128. You can convince yourselves that 85 over 117 is strictly less than tan of pi over 5, and that's strictly less than 93 over 128. So all these three triangles have the same bottom, and one of them is shorter than the other, and that is shorter than the other. Okay. By domain monotonicity, the Neumann eigenvalue, the second Neumann eigenvalue here, is going to be bigger than the second Neumann eigenvalue here. And this one's going to be bigger than the second Neumann eigenvalue here. Okay. We also construct, and I will use this later, I'm going to construct a triangle that's similar to this triangle. I'm going to call it T triple prime. And there'll be a map between the two. And I'm going to relate them through a simple scaling. So OA triple prime is 128 instead of 1. It does not matter at this juncture. At this juncture, the thing to remember is I've got three triangles. They have the same bottom OA, and one of them is shorter than the next one, and that's shorter than the next one. So how am I going to show this nodal line theorem? As mentioned, it's going to be through contradiction. I'm going to find a threshold because I need to find a comfortable bound away from the second Neumann eigenvalue on the triangle of interest. How do I find this threshold? Well, I'm going to appeal to what I just did. I know that on this triangle, the second eigenvalue is going to be bigger than the one over here. This has rational coordinates. So I can compute to relatively high precision the second eigenvalue on T prime. This has rational coordinates, and I pick a constant that's bigger than this guy. And pick it to be strictly bigger than this guy, therefore V is going to be strictly bigger than the eigenvalue of interest. Then we create certain polygonal domains in the triangle T, the triangle of interest. But we do this by looking at what they're doing. There's a map to this triangle here. So every point in this triangle can be mapped to points in this triangle. So I grow my domains by doing things here because everything is rational over here, and then I pull it back. Okay. So I'm going to create 20, actually there should be 20 triangles or polygonal domains, which are subsets of the triangle T. And one of these strange polygonal shapes I create will contain the nodal domain. Okay. Through domain monotonicity, I know that the mixed eigenvalue of that polygonal domain is going to be smaller than the second eigenvalue of the Neumann problem. Okay, so this is a theorem. This is just strictly using domain monotonicity. So lambda 1 of these weird polygons is going to be strictly less than or equal to mu2. However, numerically, I'm going to show that this lambda 1 is strictly bigger than V, the same V, and this V is strictly bigger than the second Neumann eigenfunction, value, sorry. So this line here in blue establishes the contradiction.
So I have a question.
Yes.
So regarding your second step, so find a threshold V by picking. So you said that this step is done with, I mean, any precision that you want, but the choice of the V, do you do that rigorously in the sense that you obtain a proof, or it's just you don't need a proof at this point, it's just a numerical value?
I do not need a proof. I do not need a proof. So at this point, any upper bound will suffice. Any comfortable upper bound will suffice. And I'll tell you in a second how I obtain this value. But it's one strategy is you take the triangle T, you discretize by a conforming finite element, a very high order finite element. The conforming eigenvalues are bigger than or equal to the true eigenvalues. Right? Find the first non-zero eigenvalue. Pick a number bigger than that.
Mm-hmm.
You don't need a sharp bound.
Okay.
In fact, this bound should not be sharp.
Okay.
It should be comfortable. Yeah. Okay. So I made reference to these grown domains or excluded domains. So without going into the details of the greedy algorithm and without telling you the specifics of how I generate the polygonal domains, the idea is I'm working on a triangle. All the coordinates are rational. I put down a grid on this, and the coordinates of the grid are also rational. Okay? So I have a fixed grid size, and I pick, therefore, a finite number of rational points. One point at a time, I'm going to test things, and I'm going to grow the domain as follows. I'm going to construct a so-called upper excluded domain, this green region, which corresponds to the point right here. There's one point, one point P1. Corresponding to it, there is an upper excluded region in green. The claim is that this region here does not contain the nodal domain of the full triangle. Likewise, there's another point which is associated to the P1 point here. There's another point P1L. It generates a lower excluded domain. So the nodal domain is not contained inside this region either. Okay. So I now have 2 points and 2 shaded regions, and there will not be the nodal domain in either of these green regions. So the nodal line cannot go through the green region on the top of the triangle, nor can it go through the green region at the bottom of the triangle.
Okay, so it means that they are not intersecting, not that
That's
they're
correct.
strictly inside. They do
That's
not
correct.
intersect. Okay.
They don't intersect. Yeah. So that was the first step. This is the next step. So now I have to search through the grid, but here's the second upper point. And corresponding to this, I get a new excluded region. This is the upper excluded region in green. This in magenta was the first excluded region. So now I have an excluded region, which is this magenta one, union the green one. So it's bigger. I've grown the excluded region above. Similarly, I've grown the excluded region below. Okay. So the excluded regions are growing. One is growing from the top, one is growing from the bottom. The eigenvalues that I need to compute very carefully are the eigenvalues on the so-called upper domain and the lower domain. So the upper domain will be this weird red curve, Dirichlet on this weird red curve, and then Neumann on the blue curve. Likewise, I will have to compute the eigenvalue of this shape here. So Neumann on the bits that come from the triangle, and then Dirichlet on the rest. So provided I can show to you that the eigenvalue on this weird domain here and the weird domain here are strictly bigger than V, the nodal domains cannot lie inside the excluded regions. So I keep going, I keep growing my domains, and by the time, let me show you the figure first. I think it helps understand this. By the time you're done with the algorithm, this is what happens. These are your upper excluded regions. So the nodal domain cannot lie here. The nodal domain cannot lie here. The nodal line must touch this side. It has to touch this side. It has to be a strictly increasing curve. And so the only option is that it touches the bottom. So this is what we end up with. We end up with sandwiching ourselves a thin strip where the nodal line can lie. And therefore,
why can't the nodal line touch the left vertical line?
You can check that then the one of the derivatives has to be 0, which would violate Atarburzi.
It seems that, so from the picture, it seems that there is still space for a monotonically increasing function starting from the left edge and going up to the diagonal.
Yeah, this is an artifact. We checked.
Okay.
You can grow it one more and it'll be even more obvious, but I found it hard to show on the screen. But yeah, by the time you grow one more, the excluded domains intersect. So that violates the procedure of the algorithm.
All right.
Yeah. Okay, so again, just to summarize, we're going to start with the triangle. We're going to construct a grid. Really what we're doing is we're working with the mapped triangle onto a rational triangle. We construct the grid there, and we pull back. We grow these exclusion domains. These define polygonal domains with part Dirichlet and part Neumann, where we have to compute eigenfunctions and eigenvalues. We verify on this set of polygonal domains that the first mixed eigenvalue is strictly bigger than the constant V that we've picked. So the lemma that we try to prove, and this is where we do this numerically, the identity 1, which is that the eigenvalue on the rational version of the domain of the polygonal upper domain or the polygonal lower domain is strictly bigger than the constraint V. Okay. So here's all the domains that we worked with. Here's all the polygonal domains on which we compute the eigenvalues. You could come up with a different greedy algorithm or a different search mechanism to identify polygons where you try and show that things will not work. So this is this identity that we're proving is a violation of the monotonicity result. So this will force your nodal line to go somewhere. Okay. We've generated these domains using our algorithm. Other algorithms are certainly possible. The proof certificate for this theorem is very small. It's just these 20 domains. You could find the eigenvalues using any approach you want. I'm going to show you one approach. So it's a very small proof certificate. It's not like the four-color theorem, right? Okay. So I have to show that the mixed eigenvalue is strictly bigger than a constant v for a strange polygonal domain. How am I going to do this? I'm going to construct a discrete version of the problem. And I'm going to fix a mesh size because I don't want to be refining. I don't know how much to refine. I'm going to pick a fixed mesh size. I have 20 domains. I have the luxury of doing an initial sweep through 20 domains and looking for a good mesh size. I'm going to use scaled copies of a reference element. My reference element, t hat, is going to have rational coordinates. It is going to tessellate t double prime, which also has rational coordinates. Okay. I'm going to show that the discrete eigenvalue with this fixed mesh size is less than the mixed eigenvalue, the true mixed eigenvalue. I'm going to find an approximation of this object, and I'm going to show that the approximation LH is strictly bigger than V. If I put this all together, V is strictly less than LH, LH is less than lambda 1H, and lambda 1H is less than lambda 1 mixed. So I will have the result I want. This is what I'm after. I want to show that lambda 1 mixed is strictly bigger than V. So I'm going to stick two other things in between. So the way I computed the eigenvalues, again, you could do them any way you want, but this I found to be a helpful way of doing it. I used a finite element strategy. So you can write down the variational formulation. That's easy enough. You can write down a discrete formulation. So you pick a finite dimensional vector space, a finite dimensional function space, and you obtain a discrete system. Okay. Now, if you picked your finite dimensional function space to be a subset of H1 gamma d, then you would have a conforming finite element. And in that case, the true eigenvalue will be less than or equal to the discrete eigenvalue. That's not helpful, right? Conforming eigenvalues will always bound from above. That's not helpful. We want a lower bound. So at the time that we were doing this work, there was a lovely RIM report by Schiffer, Liu, and Oishi that came out in 2011. And then it was in Sinum, I think, in 2013. And very quickly thereafter, there was a different paper by Carstensen and Gedeke. So these are guaranteed lower bounds for Dirichlet eigenvalues. So this is very nice work. This is exactly the kind of thing that we're after. But the price you pay is that you're not using a conforming method. You have to use a Crusoe-Ravier element, so a non-conforming P1 element. So because we want a lower bound, we're going to use a non-conforming element on this variational formulation. I'd like to emphasize again that this is the discrete formulation. It leads to a generalized matrix eigenvalue problem. So here's your stiffness matrix KH. Here is your mass matrix MH. Here is the discrete value lambda. You're not going to get lambda 1 exactly. you're only going to do this through iteration, right? So we're going to get an approximation LH. So let me give you a flavor of the kinds of lower bounds that people had in the literature at the time. So for the Dirichlet problem, Carstensen and Gedeke had this result saying that if you took the first eigenvalue, it was simple and well separated from the second one. And if your algebraic approximation was close to lambda 1, in other words, h has to be sufficiently small, then the computed eigenvalue through a post-processing step is strictly less than or equal to the first Dirichlet eigenvalue. So this is a lower bound. This is what I compute using a non-conforming element. I post-process it using the mesh size and a universal constant kappa, which is given. Yes, Jean-Philippe? Oh. And this object here, this post-processed object here, is less than or equal to the true eigenvalue. Liu and Oishi had a different strategy, which gives you actually much nicer bounds. Okay, so again, if h is sufficiently small, then you get a much more accurate bound, I feel, which is where you compute the eigenvalue using a Crusoe-Ravier element. You post-process it using this constant C0, which is computable, and this constant KH, which is also computable, but which requires some more computation. This object KH is destined to go to 0. We only need a crude bound. So we could have done this, but we chose to do this because it worked just fine. So the first thing we had to do was to generalize these results to the mixed problem, because we're not working with the Dirichlet problem. We're working with mixed Dirichlet Neumann. But the generalization is straightforward. So it's the same deal. If you have a bounded domain, polygonal, and you have Dirichlet on parts of it, Neumann on parts of it, and you take a sufficiently small mesh size, then this holds. The argument is standard. I'm not going to go through it. But the observation is that the function that I have on the left, it's actually an increasing function of the argument lambda. So if I define a function of the form lambda divided by 1 plus kappa squared lambda h squared, this object is increasing. So if I took a quantity lambda in here, which is strictly less than the computed eigenvalue, then f of that lambda would be less than lambda 1 mixed. All right, so we need to establish that this constant v is strictly less than the mixed eigenvalue. I compute this v by taking the triangle, computing the second Neumann eigenvalue using a P2 conforming method. I take a bound on the eigenvalue, an upper bound on the eigenvalue that I obtained. So it's 12.25. This is comfortably above the true second Neumann eigenvalue. All right. I could do better, but there's no point. So I take 12.25. I give myself some more wiggle room. So I add this constant. And there is a reason for computing this constant 3 over 256. I'm not going to go into that. So the claim is that if I let lambda be this v plus 3 over 256, and if I can find a lambda which is less than these mixed eigenvalues, the discrete mixed eigenvalues, this will imply that the constraint v is less than the mixed eigenvalue on the polygonal domain. So I'm just going to string the eigenvalues together.
Nilima?
Yeah.
So I got a question from Javier Gomez Serrano, and he asked, how do you bound lambda 2 in order to check that lambda 1 is well separated?
Ah, very good question. Very good question. I shall get to this. Very good.
Okay.
Yeah. Okay. So the validated computation. I think that maybe this is the part that I will spend like 2 minutes on, and then I'll be done. So I've got this weird domain. I need to use interval arithmetic to get provable bounds. I want to claim that the discrete eigenvalue lambda 1h is provably in this interval. Okay, L1 and plus or minus delta. And then I'm going to check that v plus a constant is strictly less than the lower edge of the interval. Because if I can do that, then, well, it's certainly less than lambda 1h. And this will establish the result. Everything in sight so far is rational. But I need to show that lambda 1h is simple. And I need to show that this eigenvalue result holds. A simple approach is to just take one matrix minus my guess times the other matrix. So kh minus lambda mh. If I show that kh minus lambda mh is positive definite, I'm done. But that would be boring. So, I mean, you can do this, and we did do this, but we did something else as well. To show that the eigenvalue is simple, I can invert the mass matrix exactly because it's diagonal, it's got rational entries. I can take the square root. I did a Hessenberg reduction of this object. So the square root of mh inverse times the stiffness matrix times the square root of the mass matrix. You can Hessenberg reduce this to tridiagonal, and I used intlab to do this. I had a fixed mesh size. So while the intervals were big, I didn't have to worry about them growing explosively big because the mesh was growing finer or anything. Like, this was a fixed mesh size calculation. Once I had a tridiagonal matrix, I used a bisection method coupled with the Sturm sequence argument. This gave me very crude but validated interval estimates of all the eigenvalues. So I get very crude estimates of the eigenvalues, but I have intervals around them. And if you look at that, then you can see that the first eigenvalue is actually well separated from the rest. So this was how we established that lambda 1 was simple. Okay. Once we were satisfied that lambda 1 was simple, we used Arnoldi to get a very high accuracy estimate. So I needed an estimate for the first eigenvalue, the discrete eigenvalue. Then I used the Lanczos result as an initial guess for an interval arithmetic computation. So I did an intlab type computation, which does a Newton in the background. I have a good initial guess. I get a great radius delta. I get a great center of the interval, and I'm guaranteed that lambda 1h is provably in there. And so this is my last slide. I've shown you half of the 20 domains on which we check things. So the gist of it is you want this column here to have strictly positive numbers. If this has strictly positive numbers, then the inequality on the top will hold. So you can stare at all these numbers, and they're all strictly positive. And so we're done. All right. So putting it all together, we've shown that by demonstrating carefully that the mixed eigenvalues in certain polygonal domains are bigger than V, we can grow these exclusion domains. We end up with a shape like this. The nodal line has to go through here. And so the nodal line does not touch the short side, and therefore upon reflection, this is what you get. And this establishes the modified Schiffer's conjecture. So now we have the full slate. All right, thank you for your attention.
Thank you very much, Nilima, for a wonderful talk. very, very well presented, especially from the newcomers like me. Okay, so I guess that Javier still has a question. So yeah, Javier, I guess you can just ask directly.
Yeah, so I have actually two questions and a comment. So the first one is, I probably didn't understand this well enough. So from what I understand from the theorem, you prove that if you have like a lambda 1h, which is the solution from the discrete system, then there is a true lambda 1 nearby, and you get like good lower and upper bounds. But in order
I just need the lower bound. Yeah, I just need the lower bound. Yeah.
But in order to check that, in the mixed case, you need to find some bound on the lambda 2, on the true lambda 2, to be far enough from the lambda 1.
Yep.
So my question is, how do you know that? Because it seems to me like there is some kind of circular argument. You're trying to prove a bound on the true lambda 1, but in order to prove that, you need a true bound on the lambda 2. And then I don't know where the circular argument sort of like stops.
Right. So, and this is a good question. So what, in the step that we took this, the stiffness matrix and then multiplied on either side.
Mm-hmm.
And then we did a bisection. So using the bisection of the storm sequence, you can get relatively crude estimates on the eigenvalues and where they are, right?
Okay.
You're guaranteed that the eigenvalues lie within an interval around these crude estimates, okay?
Mm-hmm.
You don't need
but the eigenvalue, you mean the true eigenvalues or the eigenvalues of the discrete system? When you say eigenvalues now, you're referring to the discrete ones, say? Or
okay, good question. So to get, okay, so you want a lower bound, because, so I don't know how to best do this. You want to show that lambda 1 and lambda 2 are well separated, for which you need a decent lower bound on lambda 2.
That's right.
Right?
Yes.
Okay, it would suffice if I could provably bracket lambda 2.
Okay, yes.
Right, that's what I need to do. Okay. So the eigenvalue enclosure statements that I showed you, they are valid not just for the first eigenvalue. Okay. The slick way to do it, the really slick way to do it, would be to do what Xufeng would do, which is to use his post-processing step to get very good, like tight enclosures. You don't need those tight enclosures. So all you need to do is get—
One remark for this discussion. Because I think this is related to the lower bound from FEM. So
yes.
I think there's something misunderstood about the result from FEM result. So first, okay, I prepared some comment. So let me then comment to everyone. So to give rigorous eigenvalue bound, so the separative condition needed in the Castaneda result is essentially not needed. We don't need this condition as it proved in my later paper.
Absolutely agreed. Absolutely agreed. Absolutely agreed. So that's exactly what I was saying. So you could do all of this. Okay. Here are two statements. You could prove the result I need without appealing to any of this. You construct the stiffness matrix. You take the guess lambda that you're trying to show. So you take the stiffness matrix minus lambda times the mass matrix. Show it's positive definite. You can do that within SAGE, for example, using exact precision. These are matrices with rational entries. You just need to show it's positive definite. So you do an LD-LD composition, you're done, right? Just look at the diagonal. Then you don't have to do all this other business.
Well, but this is for the first, right? If you want to do the second, then the LD.
I don't care about the second, right? Like
okay,
I don't need the second. I just need to show that the first eigenvalue is strictly bounded below, right? So
may I make a remark on this discussion? You see, when you have a rough lower bound on the second eigenvalue, this is very much in the spirit of the Lehmann-Görisch method, which is a very general method for computing lower eigenvalue bounds. And so the special case for the a rough lower bound for the second eigenvalue, you immediately get a precise lower bound for the first eigenvalue using the Temple quotient. You see, the Temple quotient is the version for lower eigenvalues, so to say, while the Rayleigh quotient is the quantity for upper eigenvalues. So when you have a rough lower bound on the second, then you can use the Rayleigh quotient, and you do not need any non-conforming elements. You can do everything with conforming elements.
I still need a lower bound in the second one then, right?
So that's right. So you need a very rough lower bound on the second. So if you have that by your bisection method, then you can use very easily the Temple quotient.
We tried that, but we needed to get all of the eigenvalues to be bigger than this number V, right? So V is loose, but it's not that loose.
Yeah, but it's no problem. So you see that the Temple quotient gives a very precise lower bound, even if the lower bound of the second eigenvalue is a very rough one. So then nevertheless, you get a very precise lower bound on the first one.
Well,
so it's
okay.
even optimal. So Lehmann in his original work has proved that this bound is optimal. You cannot do better if you know certain quantities and not more, roughly speaking.
This was not our experience, because the lower bound that we got on the second eigenvalue was, like I mentioned, through this very crude strategy using a bisection. But yeah, sure.
Yeah, but you did not use the Temple quotient.
No, I did not.
Yeah, that's the point. The Temple quotient gives a very precise lower bound, right? It's more precise, and I think Xu-Feng will confirm that. It's more precise. So the Lehmann-Görisch method or the Temple quotient gives a more precise lower bound than Xu-Feng's method, right?
So this would be good. I'm not claiming for a minute that the finite element strategy we tried is the best way to do it. That's not the point. The point is,
no, of course, it's not the point in your lecture. That's clear. But I just wanted to make clear that this is so to say, a very special case of a very general approach.
Sorry, I had another question. How big are the matrices? Like, what's the size of the mesh?
64 by 64.
Okay. Yeah, and okay. So also a comment on, like, without having, like, once you have the matrix and you want to construct the discrete eigenvalue and the bounds on the eigenvalue without having to go through LDL. So LDL is nice because you're looking for the first one, but if you want to go higher up, then it doesn't work anymore. And
Sure.
the Sturm is super slow.
Yeah, absolutely. But we had time.
Okay. So I mean, I've tried myself, and something we tried that worked like the best was to compute a non-rigorous basis, like to diagonalize non-rigorously and then prove the stability of that. So show that because the advantage is if you're looking for, say, the 10th one and your matrix is 1,000 by 1,000, you only need to do very well on the first 10, and the rest you can do very badly. So
right.
As long as you almost diagonalize in these 10 bad directions, the rest you can tolerate huge errors. So then
right.
you can do that diagonalizations very fast, because you can do like partial diagonalization or something like that. And then all you have to show is that you have an eigenbasis very close to the one that you found.
Right.
And that's a lot faster, because you can do like the scoring theorems or something like that. And again, it's only, you're looking in a very small subset of directions. So that is what work does for like the fastest. We had something which was of the order of 500 or so elements, but just, you know.
Yeah, no, this was a deliberately tiny calculation.
Okay. Thanks.
So what, the comments that we got from the referees were, the first time was, I guess it was sent to somebody that was not familiar with how to build finite element matrices. They did not like the idea of a matrix whose entries they did not know. So we actually had to enumerate what the entries were. And that's when we realized that, oh, okay, you can actually get away with a smaller mesh size than we had initially planned. You can compute the entries by hand. That's how we actually build them. We build them in NumPy. But then you have to worry about zeros in places that you don't want them. But you can actually build it in Sage using exact arithmetic.
Yeah, you have to go to the pain of going to rational. It's slightly unpleasant, but
I mean, we have domain monotonicity, so it worked for us.
yeah.
May I ask another question precisely on that point concerning the domain monotonicity?
Yep.
So you see, you had these three triangles. That was T. You had the original one is T. Then you had T prime and T double prime.
Yep.
They were well, by slightly changing the angle. But so you have you're looking for Neumann eigenvalues. So on each of the edges of these triangles, you have Neumann boundary conditions. Is that right?
That's correct.
But then you have no domain monotonicity.
I'm not looking for domain monotonicity for the Neumann eigenvalue. I'm constructing polygonal domains within T double prime, which contains T, and I have monotonicity of the mixed eigenvalues.
And but the edge of this triangle was changes, right? So there's a change in let me call it diagonal. The diagonal one changes, and on that one you have Dirichlet eigenvalues. Otherwise, I don't see.
No, so let me just try and share the screen again. All right, where did we go? Okay, so let me try and do it with reference to this figure here. Okay, so if I was on this domain and I keep the edges of the blue triangle fixed, I'm growing my domains inside here. So I use a domain monotonicity argument inside here. So this is one of them.
Yeah, okay.
All right. The other one uses this result. So the Neumann pieces are as described here, and the Dirichlet pieces are separate. So the Neumann piece of the one domain is a subset of the Neumann piece of the second domain. I'm doing so what I'm doing with my triangles, let's see. Right here. I am keeping the bottom fixed and I'm stretching this side.
But the diagonal changes. So that
the diagonal changes, but in the monotonicity that I need, so there's two forms of monotonicity that I need. I need this one, and I do not think this is controversial.
But this is, so the mu is Neumann eigenvalue, or what do you mean by mu?
Yes, it is the Neumann eigenvalue.
But your argument with the domain, I cannot recognize how your argument works with the domain monotonicity, because there is a Neumann part of the boundary, namely the diagonal, which is changed.
So this guy is going to be stretched within this guy.
Yeah, but the A stays the same. So the right lower corner stays the same, and the left upper corner moves upwards.
Yes.
And that means that the diagonal changes.
Yes. So this eigenvalue here is going to be smaller than this one, right?
Yeah, why? This is, you're using a domain monotonicity for a Neumann problem.
So I can just extend by 0, right?
No, not if you have Neumann boundary conditions, you can't do that.
So if I have something going in flat, I can harmonically extend it. This is, okay, let me show you this.
Yeah, but this is a completely different argument. This is not monotonicity. If you want to harmonically extend, then you have to reverse the whole proof.
So the details of the proof are in the paper.
Yeah, but I cannot recognize, it's all I can say is I cannot recognize from your domain monotonicity, where you only change Dirichlet part of the boundary, I cannot recognize how you apply that to the T prime, T double prime situation, because their Neumann part changes.
Okay, so I think, let's see where you are. So is this, So phi of dm, so dm is a domain on the triangle. Phi of dm is the mapped image on the t double prime. Is this
No, I'm just questioning your inequality mu of t prime bigger than or equal to mu of t bigger than or equal to mu of.
This is an eigenvalue on a nodal domain, which has to be equal to mu2 of t. This is all I need. I don't need anything else. I don't even need the monotonicity of the Neumann eigenvalues, right?
Can you please go to the next transparency where you have this? No, then it was the previous one. So where you had here the last line, line. This is very simple. Just the last line. This inequality between the mu's. I don't understand.
I don't believe this is necessary, and it may not be true, but it doesn't matter. I don't need it. Right? What I need is this.
Okay, so that's too. I can't recognize this last line. When you say you don't need it, okay, then.
Yeah.
But you see that in the second step, key steps of proof of theorem, in the second bullet point, you're also using mu of t prime bigger than or equal to mu of t.
So this we have actually got a lemma in the paper, which shows that for the particular form of stretching that we employed, this is actually a valid statement.
All right, but not by domain monotonicity.
We call it domain monotonicity.
Well, no, okay.
Okay. Well, I propose that this specific discussion either is continued like separately, or I mean, maybe reading a paper could be. You could have the last details. So are there any, I can see some comments here, but it's mainly for thinking. Are there any other questions?
I actually have another question if there's nobody else before, because I talked already much.
Maybe you have rest. Let me read the question. Okay,
yeah.
So very nice talk and very nice constructive proof for this theorem. So one remark and one question or some suggestion. One remark is about the eigenvalue bound from FEM. So you repeated it many times. So the mesh size is sufficiently small enough. It's not small enough. In fact, so the current result is holds for arbitrary mesh size. Although the bound is raw, but it works for arbitrary mesh size. We don't need it to be small enough because we cannot confirm whether it is small enough.
Yes. So this is. I was referring to your paper from 2013.
2013.
Yeah.
Even in that paper, so yes, there one condition.
So there you need the quantity m sub h. Like I remember, there is this computable quantity m sub h.
It is totally remote. Yes.
Yeah. So the m sub h needs to be sufficiently small. Yes.
Because some old result, it is totally improved. Okay. This is one remark. Okay. The other thing is about the question or some suggestion. So here you consider the exact lower bound, okay, by FEM or by other method. So also we can give rigorous bound for the eigenfunction, right?
This is this is more recent work, and this is definitely possible. Yeah, that would be another approach.
Idea not so new, but yes, some sense recent result. So we can give rigorous bound for the eigenfunction, even they are a clustered eigenvalue, cluster eigenfunction, but we can give rigorous bound.
Yeah.
I think because you see we can get an eigenfunction. You see that the eigenfunction the value is positive on the boundary, and we can give the error in L2 norm or H1 norm, and maybe further result. So we can measure the difference between the approximate eigenfunction and the exact eigenfunction, and then maybe give another proof.
I think that would be actually very clever. So if you could do it, yes, there's many different ways to do this.
In L infinity in R2, so you need a little bit stronger than that.
But I guess Schiffer is saying that if you computed the eigenfunction on a triangle, I mean, it's fairly benign. Do you have reasonable in L infinity? Of course, if you could do that, that would be brilliant. Then you don't have to go through all the hassle of generating anything.
I have one preprint paper. You can find it in my homepage. And also for the comment you see about the infinity norm, I think it is something like this. So eigenvalue problem, something related to the boundary value problem. So we can give infinity norm for the error between exact solution and the FEM solution. So.
Okay.
Yes,
okay. I just pointed, since you said L2 over H1, this is the why I said that doesn't give well infinity.
A very idea, but maybe I think it will be helpful.
Yeah, no, absolutely. So the slickest thing, of course, and this is what I'm hoping for, is that somebody is able to furnish a proof for this modification without resorting to numerics of any kind. All right, that would be simplest. Because for the triangle, for the square, for the hex, for everything except the pentagon, you can find relatively slick proofs. The fact that the pentagon is its own thing is irritating.
Okay.
So there was, before going back to Michael, there was a question from Alexander who said, when did you use a learning algorithm mentioned in the abstract?
Oh, in the choice of the points. So you could actually march through all the points on the grid to grow the polygonal domains. But that was too much work. And besides, one of my collaborators likes game theory, so he developed this algorithm. You could do it some other different way.
Okay. Okay, so Alexander says thanks. So, so Michael, you still had a question or comment, I believe.
Well, yeah, actually, that goes back to the question which I put already during the talk, and then I was quiet because I didn't want to interrupt the talk too long. But actually, I still don't quite understand this argument where you answered it's an artifact. So that's at the end of this greedy algorithm. You had this upper region which excludes, so the nodal line cannot go through. And there's this lower part where it can't go through. Yes. But there's always some area near the corner, near the left lower corner, which is not covered by these two excluding regions. And that's why I cannot understand how you can exclude that there is the curve going through this corridor and then touches the left line.
So
maybe can you show this picture again? So
yes, I can show this picture again. All right.
No, I don't. I mean the one where you yeah, this one. Yes. Yeah.
Right. Okay, so do be aware that this is not this is just using TICX. So this is not a Cartesian grid.
Yeah, but how can you, so there's, as long as the left upper excluding region does not cover the whole left vertical line, there's always the chance to go through this corridor with a monotonically increasing function.
So the next one that you grow will cover this entire side.
Well, but
we'll cover the entire side.
But that's where you want to.
The node line must touch the side.
Yeah, but you want to exclude that it touches the vertical line on the left, right? That's what you want to exclude. And how do you exclude that?
So if you grew this one more, then you would not have a nodal domain. So there would be a violation of something, right? So now your nodal domain must lie or cannot just lie within this region here. So your nodal line cannot be like here. So your nodal line can at best be in this shaded region out here.
Yeah.
Right? But you also have to look at the polygonal domains that go along with these excluded regions. So putting that all together, you arrive at the contradiction that you cannot have the nodal line touch this side. And once again, Michael, I do appreciate that looking at this on a slide is not going to be satisfactory. And again, I'm going to refer you to the paper where we've tried to lay this out carefully.
Okay, so you're saying that this picture does not give the answer, but there is another answer which
this is intended to show you that the algorithm stops in a finite number of steps. I haven't shown you the algorithm. I haven't shown you how we're selecting these points. This is intended as a proof of, by picture. This is not a proof. This is just to illustrate that this thing terminates, and then yes, it is conceivable that the nodal line is going that way, right?
Mm-hmm. Okay, so since, well, of course I don't have your paper in front now, so I can't further comment. So I have to believe you.
Okay. So, are there any other questions or comments? So 25 minutes of questions. More questions or comments? Okay, well, if not, well, first of all, thanks a lot, Nilima, for sharing your research with us, and thanks for waking up so early. For you, you had to wake up before, I guess, before 7, and then getting ready around 6 something to give a talk, and having after that to answer for 25 minutes of questions. So many thanks. It spurred definitely some interest. And you can look in the chat. There are many nice messages of thanking. So yeah, so thanks a lot for coming. Thanks, Nilima, for giving us a great talk. And we're going to see you next week with the talk of Daniel Wilczak, who's going to talk about chaos in the Kuramoto-Shifashevsky PD. Okay, so thank you very much.
Everyone.